Alright, so this is an example. This is example E3.1 in the statics companion, which is example 3.4 from the textbook. And here's the problem statement. You can see that we have a structure that consists of a collar here at B that's free to slide along this rod AC, and the rod's at theta equals 30 degrees relative to horizontal, and then mounted on the collar is this frictionless pulley, and that frictionless pulley has a cable that supports a 5-pound weight here and is fixed over here at location E, which is at the same Y location as B, so it's horizontal. And then you have this bar BD that's at some angle alpha, and that bar is also exerting a force. And the question says if alpha is equal to 0, so that's the case where the bar is horizontal, then determine the force in the bar needed to keep the system in equilibrium, and then vary alpha to see what value will provide the smallest force in the bar. Alright, so that's the problem, and I guess I'll give you time to go off and maybe try to solve it, and then come back and we can go through the solution here in case there's any questions. Alright, so we're going to analyze this problem basically in the same way that was done in the book, except for we're going to make sure that the angle of the bar alpha here is a variable that we can adjust in order to carry out a parametric study that will allow us to look at how that angle affects the force FBD here. So we're going to do a free body diagram on the collar. So that free body diagram is shown here. The free body diagram basically just says that there are 4 forces on the collar. Right, there's a force due to the cable that is pulling down, and the tension in that cable is just the weight that it's holding if everything is static. So a free body diagram on the weight itself would just say that the tension is equal to the weight. And then there's also a force pulling from the cable to the left, and then there is a force from the bar, and that force could be in either direction. I'm going to draw it here as if it's the bar is pulling on the collar, so that's FBD, and that's at this prescribed angle alpha. And then finally there's a reaction force from the bar onto the collar, and because the bar itself is frictionless, so the collar can slide along the bar without friction, we know that there can be no component to that force that is in the direction of the bar. So the component is only normal to the bar, as I've drawn it here, R. So those are the 4 forces, and we can do this using either scalar parameters. So not think about it in terms of vectors, just think about doing it with scalar variables, or we can do it with vector variables. Either way is fine, and we'll do it both ways. We'll start with scalar variables because that's how they did it in the book, and then we'll come back and do it again with vector variables because that is kind of interesting. We should get the same answer. So scalar vector variables would say that we want to sum up the forces in the x direction, and that'll give us one scalar equation, and then we want to sum up the forces in the y direction. That'll give us another scalar equation, and set both of those equal to 0. So let's start with the sum of the forces in the x direction. So if x is to the right, then I have a negative t here. I have a negative r times the sine of theta, that's this component here, and then I have FBD times the cosine of alpha, and that's this component here. And then if y is up, I'm going to have negative t pulling down from this force. R cosine theta is the y component of this reaction force R, and then minus FBD times the sine of alpha is the component from the bar. So at this point I have 3 equations, and there's 3 unknowns, right? T and R and FBD, so I should be good to go, and I can go ahead and enter these into E's and solve them there. Alright, so let's go ahead and solve this in ease. So the first thing to recognize is that I'm going to be using trigonometric functions in ease, so I need to specify the units that I want angles to be in. So I do that with the $unit system directive, and I'm going to use degrees because degrees are what was given in the problem statement. And then we'll enter some of the known values. So I know that the weight is 5 pounds force. Alpha is the angle of that bar, and we're going to vary it eventually, but for now it's 0 degrees. And then theta is the value the angle of the bar relative to horizontal, and that's 30 degrees. So those are my inputs. And then I have these three equations, right? The first equation is that the tension is equal to W. Second equation is that summation of forces in the x direction has to be 0, so minus T minus R times the sine of theta, plus FBD times the cosine of alpha has to be equal to 0. And then finally the summation of the forces in the y direction has to be 0, so minus T minus FBD times the sine of alpha plus R times the cosine of theta has to be equal to 0. So that should be three equations and three unknowns. And if we solve, so calculate solve, or F2, here's my solutions window, and yeah, I have a solution here. I probably should set the units, so that's pound force. This is a force in pounds force, and this is another force in pounds force. So there's no unit issues, and what I find is for these conditions, here are my two unknown reaction forces. Okay, so we need to vary this alpha for part B and figure out what value of alpha causes FBD here to be minimized, right? So I can do this a couple ways. I can just comment this out and make a parametric table, or I can use a $if not parametric directive. So I think I'm going to go ahead and do that. $if not parametric, and then $and if. So now if I just solve as I did before, this equation will be in there and I can get a solution. But if I solve using a parametric table, then this equation will be removed, and therefore I can solve my parametric table. So let's see, let's make a new parametric table, and in this parametric table I'm going to vary alpha, that's my independent variable, and I'm going to look at the magnitude of FBD, that's my dependent variable. So we'll add those two variables to my parametric table. And now let's vary alpha over some range. Let's see, I'm going to vary it from something like minus 50 to 50 degrees. So minus 50 degrees to 50 degrees. Hit OK. And now when I solve my table, which I can do with this green button, or calculate solve table, these are the values of the force in that bar BD for every value of alpha. And just looking at it, I can see that an alpha around minus 27.8 minimizes this, but you know, I can make a plot, maybe get a better idea how this varies. So plot, new plot, XY plot, and let's see, I want x-axis to be alpha, I want the y-axis to be FBD, and we'll hit OK. And yeah, there's my plot. You can see minus 30 or so is what minimizes FBD. In fact, if I want to, maybe I should even zoom in a little bit, so I can zoom in with this zoom selection. So we'll go right here and maybe zoom in on the region I'm interested in, and yeah, it becomes even more obvious that sort of minus 30 is the optimal angle. So it's also interesting to solve this using vector variables rather than scalar variables, and that's instructive. So this is the free body diagram, but I have now each of these vectors, right? So there's force BE, which is the force from the cable pulling it to the left. There's W, which is the vector force pulling it down. And then there's FBD and R, which are the vectors corresponding to the forces on that bar, and then the reaction force between the collar and the bar. And the vector sum of these four forces has to equal 0. And here 0 means the zeros vector, right? So that's the equilibrium force written in vector form. So let's go ahead and try to solve it using vector variables. So I'm going to start over again with a new ease program. Okay, so let's see. Again, first thing I'm going to do is specify the unit system as degrees, which is a good idea. I'll enter my same input. So W is 5 pounds force. That's the weight. Alpha is 0 degrees. And theta is 30 degrees. Okay, so now I'm going to again specify that the tension is equal to the weight. That's the tension in that cable. And that I have 4 vectors that have to add up. So let's define 4 vectors. So I do that with the dollar vector. And these are 2-dimensional vectors, so I'll use dollar vector 2D. And the 4 vectors are R, FBD, FBE, and W. And now I just have to assign these vectors as best I can. So R is, let's see, this is a vector where I know the angle. So vector assign polar is probably the best one to do here. So vector assign polar, and let's see, the magnitude is the mag R, that's a scalar, and the angle is the angle relative to the x-axis. So that's going to be 90 degrees plus theta, right? So theta plus 90 degrees. All right, and then I have FBD, right? So FBD, again, this is one where I know the angle of the force, so vector assign polar is probably the best way to go. So this is, oh, I forgot a T there. Okay, vector assign polar. This is the magnitude of FBD, and it's at minus alpha relative to the x-axis. Then I have FBE. So FBE is off to the left. It's in the negative x direction. There's different ways you can do that, but let's just do FBE equals vector assign. And here I'm going to have, let's see, the x component is minus t and the y component is 0. And then finally W, so this is straight down, so vector assign. In this case, the x component is 0 and the y component is minus t. So that should be all my vectors, and my equilibrium equation written in terms of vectors is just that the sum of these have to be 0. So FBE plus FW plus R plus, what's the last one, FBD has to be equal to, and I can't put 0 here, I have to put vector zeros because that's the 0, 0, right, in 2 dimensions, x and y. So this is actually, if you think about it, 2 equations. This is an equation for all of the x components and then another equation for all the y components. And so hopefully, if we solve, so calculate, solve. So let's see, what's our problem here? The problem is this equation right here. So this equation right here, it doesn't like, oh, and I guess I see why, and that's because this is FW, but up here I called the vector W. So it looks to me like I'm trying to assign a vector variable to a scalar, which of course you can't do. So let's change this to FW, like that, and try again. Calculate, solve, and this time it seems to like it a lot better. And here's our solution, and actually should be the same as what we got previously, right? 5.774 and 7.877. So let's go ahead and make sure units check. So I'm just going to confirm the suggested units for all of those vectors, and then we know that this has to have unit to pound force, as does this, and then finally as does this, pounds force. And at this point there should be no units, so no unit problems, and everything looks good. One thing that using vector variables allows us to do is to develop vector plots, which is really handy. In this case, And one thing we can do is make a vector polygon. So as discussed in the book, the vector polygon ought to close up on itself because all these vectors have to add to 0, right? So if I plot them head to tail, they should go back to where they started from. So let's go ahead and do that. Yeah, okay, so plot, new plot, vector plot, and these are 2D vectors. So the way that I want to do this, I think, is I'll start with the first one at the origin. So I'm going to plot FBE starting at the origin, and I'll plot it. And then, let's see, the next ones I want to start from the head of the last vector. So let's then add the vector R. Let's add the vector FBD. And finally, let's add the vector FW. Plot. And those are all the vectors I want to plot. So if I hit done, yeah, there's my forced polygon. Right? You can see I start here, and as I add up all 4 vectors, I end up where I started from, which means that the sum of these vectors is actually equal to 0, which is handy. And one nice thing you can do now is vary the angles and see how this polygon changes, which sometimes is really helpful if you want to understand, why forces are changing sort of the way that they are.